Hello, in this video I'm going to walk you through some examples from chapter 1 of the EOPL textbook. Here is the URL to the repository, and you can click on chapter 1 and then examples. I've collected the source code here so you can try it yourself by copy pasting it into Dr. Racket. So here in a previous video I have shown you that a list is really a sequence of cons pairs chained together like this. This is the backbone. If you trace the cursor, it always takes you to an empty list, and then each element can be anything, can be another list, can be an atomic value, so on and so forth. But for it to be proper, it's gonna have a backbone like this. So a list is also recursive defined like this using this grammar. So a list can be an empty list or a symbol if it's a list of symbols with cons pair. Okay, so a pair that with the symbol as the first element, and then another list of symbols. So this is recursively defined, and so you will see that all the algorithms we use for list processing are recursive in nature, because here is the principle. Or the structure is defined recursively, so a recursively defined procedure matches this shape and is usually more intuitive to use to process this kind of structure. So here's the thinking. If we can reduce the problem to a smaller subproblem, a smaller version itself, we can apply the same procedure, the procedure we're defining, to the subproblem to solve the overall problem. Okay, so I'm going to copy the list length program and put it in my Racket, paste, run my definition, and then this will execute, interpret my definition. So we have a list length procedure. So given a list of symbols, it's gonna tell me how long this list is. Okay, so we have a list of lists, but at the top level we really have a list of 2 elements. So that's the answer is 2, and similarly here. Okay, so how do we solve this problem? Well, our procedure is recursively defined, right? So list length is defined in terms of length. So we're applying that sub-problem principle, right? This is actually, we're following the definition, the recursive definition of a list. So given a list, if it's empty, right, it's just simply list possible. It's a list, right, the smallest list, and then the length is 0 by definition. Okay, we know the answer right away. Otherwise, it's gonna be the first element. Okay, so the length of the list with the first element removed, right? This is the remainder of the list, the cursor of the first cons pair, as shown here, right? We remove this, we use cons, a cursor to find the remainder of the list. The length of this overall list is going to be the length of the remainder plus 1, right? So, and then that's it, right? What is the length of the remainder of the list? It's the same procedure, and if it's empty, then length is 0. Otherwise, it's gonna be the length of the remainder of the list. So the rest of the list plus 1, right? The list with the what we get as a parameter with the first element removed, and we get that length, and then we plus 1. Okay, so I'm gonna run this program, and we'll trace it to develop some understanding. Oh, can't do that. That's just so I need to run just the program, not the output. So that's 3. If we use the trace facility, we can need to run it again, refresh the definition, and then we run this. So as you can see, this is recursive. List length is called 1, 2, 3, 4 times. So we call it the first time, and then it's recursively calls the same procedure on the remainder of the list, and then on the remainder of the list, and then to the end it's the empty list. But every time we make the recursive call, there's a pending operation, right? So every time the recursive call returns, we need to do something before we can return it to the previous call. So every time we add 1, so this gives us 0, but then we're gonna add okay, so and then we're gonna add 1, so 1 becomes the result of this procedure call. And then recall that after this procedure call, in the greater context, we have add 1 there. So we add 1, so 2 becomes the length of this list. And then there's outside of this, before this procedure call, we have another pending operation which is +1. So 3 becomes the result of list length of A, B, C. Okay, so that's how the recursion works. We have a recursive defined data structure, a list, and then we have a recursive procedure that this is called a curder down pattern. So we define this recursive procedure to fit this recursive data structure, and then so that this kick off a recursive process that will solve the problem for us because of how list is defined. So similarly, we can have the nth element procedure, so which given a list and the index, okay, so the third, so it's a zeros, first, second, third, so it's a 0 based, and zeros, first, third, 0, first, second, third, right? So that's right. And then as you can see, the shape looks really similar, except for the logic. So what we're doing here is, let me trace it. Okay, so here, given a list, if it's empty, then yeah, so we're going to report an error. So with n, and then we have a helper procedure that prints out meaningful message. So we'll skip this for now. But if it's not empty, then if n is 0, okay, given the list, we want the zeros element at 0's index, and it's not empty. Well, we know the answer right away, right? It's going to be the car of the list. Like, again, recall a list internally looks like this. Okay, so there's a start with a const pair. If there's a const pair, we can always get the first part, which is the first element of the list. It is the car of the list. So that's why we can do this. Okay, otherwise, to get the nth element of the list is the same as getting if n is not 0, is the same as getting the n minus 1th list element of the kernel of the list. Right? This again is based on the recursive definition of a proper list. Right? So as you can see, we recursively call till we get n becomes 0 and the list is not empty, we just get the car of the list. So if before we get n equal to 0 and the list becomes empty, something is wrong, right? Our index is out of bound, it's too large, right? So let's run this. Okay, so we have a trace. So that's, you can see we call nth element 1, 2, 3, 4 times. till the index becomes 0, and then the element we're looking for is the car of that list. Okay, so this is a tail recursion, because in the recursive call, after the recursive call, there's no pending operation, so it doesn't grow the depths and in-depths, and it just does that. So I also have an example here. It's from the textbook. So there's another implementation called list_ref that does exactly the same thing, and if you pass in a index that's too large, you get an error. Okay, so yeah, take a look at this, and this is you need to really understand how this procedure works, how recursion works, and how this can work on any proper list, something like this internally. Okay, I hope this is helpful.